Hi everybody, this is Dynamics and Number Theory seminar, our second meeting, and we are happy to have Barak Weiss from Tel Aviv telling us something about classification and statistics of measures on spaces of cut and project sets.
Okay.
Thank you.
All right. Thank you very much, Dimitri. Thank you all for coming. As you can see, this is joint work with Rene, Ruehr, and Yotam Smilansky. Yotam is in the audience. I don't know if Rene is, but so I'm also grateful to the organizers, first of all, for inviting me and also for changing the timing because the previous semester it was impossible for me to join. So let's get started. So as Dima said, please interrupt me, stop me if things are not clear. So this is intended to be sort of a high-level talk with not so many proofs at the beginning, and our results are somewhat technical, so maybe not all the details will be there. So please, so there might be a lot of vague points, so please don't be shy and interrupt whenever I'm being too vague. So this is about cut and project sets. Cut and project sets are a class of discrete sets, and they live in d-dimensional Euclidean space, which we call physical space. So there's a physical space, and there's a bigger space, which is Rn, which is a direct sum of this physical space, and another space which is sort of invisible. It's called internal space, and it's m-dimensional. So we have a kind of a direct sum decomposition of Rn into two spaces, and we have the corresponding two projections. And to construct a discrete set here in the physical space, we take a lattice or a grid. A grid is just a fancy word for a translated lattice living in n-dimensional space. We take a subset of the internal space called the window. We cut the lattice, that's cut and project. So we cut the lattice on the kind of slice that's the preimage of the window. And then we project the corresponding set that we have onto physical space. So here's a picture that is supposed to help you understand what's going on. So the cut and project set are these blue dots that you're seeing along this one-dimensional line. This is a construction with n being 2. So the total space is 2-dimensional and physical space is 1-dimensional. So physical space is this line you're seeing over here. The lattice are these regularly placed points. It's the integer lattice. This is the direction of internal space. This is the direction of physical space. The window is this reddish region. The preimage under the projection to the window is this slice that I'm moving the beamer pointer in. You're intersecting this slice with lattice points. That gives you these points along this line, and then you project them onto the physical space and you get a discrete set. And so there is a lattice in the background, but this, depending on the direction of these spaces, this is typically an aperiodic set, and it's kind of a classical model of so-called aperiodic order, and it's been well studied in many domains in mathematics. And that's our object of study today, these such sets. And here's a famous example, which is was made even more famous recently when Penrose received the Nobel Prize. Penrose also had a mathematical contribution, and this is this tiling construction. So what's a Penrose tiling? You take two sets. One is this thing called a kite, and one is this thing called a dart. They're both quadrilaterals. If you were to fit them end to end with this edge touching this edge, you'd get a rhombus, which obviously tiles the plane, but you have these markings, this blue and red marking, and you're only allowed to attach these quadrilaterals to each other so that the markings extend continuously across these polygons. And that prevents you from adjoining this side to this side, but you can adjoin this, let's see, yeah, you can adjoin this side to, to this side by flipping. I'm sorry, this is kind of confused me for you. You can adjoin this side to this side, I meant, by rotating this dart counterclockwise by more than 180 degrees, and then you'll get some attachment that's legal. And the amazing thing that Penrose discovered is that using these two shapes, you can actually tile the entire plane, but only aperiodically. And here's a big piece of the plane that's tiled using these local rules. Let me zoom in for a moment. And so you can see that it's made of these kites and these darts. And if I zoom out again, you see that you sort of see things over and over again, like this thing is repeated over here almost, or over here almost, but not identically, and there's no periodicity in the shape. So these objects that you see locally are called patches. They're going to play a role in what comes up next. Okay, so that's the famous Penrose tile, and it's a fact that the vertices of these polygons can also be described alternatively, instead of using this tiling mechanism, by using the cut and project mechanism that I mentioned a few slides ago. So what do we do in this project? We're trying to describe probability measures that live on cut and project sets. In other words, it's a way of assigning a probability distribution to cut and project sets, which is affine group invariant and ergodic. So the affine group, that's the group of affine transformations of d-dimensional space. Yeah, is there a question?
You are mute. Can I use your copy?
So the affine group, the d-dimensional affine group preserving volume, is acting on d-dimensional space. So it's acting on these sets. It maps sets to sets. And therefore, we have a notion of invariant probability measures on these sets. And we're trying to describe such measures. And one of our main results is a complete classification of such measures. And using that, we address sort of a general question of what do these sets look like typically for such a measure. And when I say typically, well, they're just discrete sets in RD, but what can we say about their large scale geometry? And you're going to see that we get analogues of well-known results of Schmidt that were known for lattices for these cut and project space for counting points and counting patches. So we'll get to that at the end of the lecture. And so I want to slowly give some information so to make this possible to state a rigorous result, more or less. So first of all, what do I mean by a space of discrete sets? I'd like to topologize the collection of all discrete sets in some way. And then using that topology, I'll describe a Borel sigma algebra, and that'll be a prerequisite for discussing measures. And so instead of just topologizing discrete sets, I can just topologize all closed subsets of RD. So this curly C of RD stands for all closed subsets of RD. And there's a metric, a natural metric on this collection, which is called the Chaboty-Fell metric. I'll define it in a second. Using that metric, you can talk about closures of orbits. This is the orbit under the translation group. You can take a discrete set and translate it around, and you get something called a tiling space. More generally, you could take orbits for the affine group or for other groups acting on the plane, and you get collections of closed sets, and then you can take their closure with respect to this topology. What is the topology? The Chaboty-Fell topology, it's actually a topology given by a metric, and without going into too many details, two sets are close in this topology, in this metric, if they almost coincide up to epsilon in a very large ball of size approximately 1 over epsilon. So this is the formal definition, and it's a compact topology on this huge collection of all closed subsets. I just gave you this topology because I think it's the easiest one to work with, but there are many other topologies that people use in the literature, and actually many of them coincide when we discuss cut and project sets. So let me give you some background, historical background on why one would want to discuss this renormalization by the action, for the action of this group ASLDR. First of all, what is renormalization? Whenever you have an invariant probability measure, you can talk about things that you see over and over again when you apply elements of the group action. And that was well studied for another action, which is just the action by dilations. You can take a discrete set and you can just enlarge it, dilate it. And that's an R star action. And that's classically studied in the following setup. So this is just kind of historical background about renormalization dynamics for tiling spaces. Here's a substitution rule. You take these three triangles on the left and you inflate them by some factor, make them larger. And then there's a subdivision rule that tells you how to obtain the inflated tiles from the original tiles by some translation. So you see that this inflated tile contains 2 copies of itself rotated, 2 copies of this guy rotated, 1 copy of the small guy rotated, and similarly for the other ones. If you repeatedly apply this rule, so you make the object larger and then subdivide, you get a tiling again. That's exactly what we would have seen with the Penrose tiling if we would have followed the kites and the darts. They also can be described in terms of these substitution rules. And so this is an example of a tiling that you get. Now, this kind of tiling, you can understand what happens to it when you do exactly what I'm doing now, which is zooming in or zooming out. When I do that, I'm dilating, and I could think about what would happen if I was to dilate and subdivide, and that's a dynamical system. It preserves a natural measure, and understanding that measure is a vehicle for understanding what this type of tiling looks like in the large scale. That's kind of a classical technique in this field. So that's R star renormalization. Please stop me if I'm going too fast, because this might be new to some people. So that was sort of a very vague description of R star renormalization, multiplicative group of real numbers. What we care about is this group. So this is the group of affine maps of physical space to itself. An affine map consists of a linear transformation and a translation. And we want the linear transformation to have determinant 1. So that means it preserves the volume and the orientation. So that's this group ASLDR is the group that we care about. It's acting on these spaces. And I want to mention 2 historical examples when this ASLDR action and its dynamics were used for understanding discrete sets. So there's a sequence of beautiful papers by Marklof and Strombergsson, and they analyzed something that they called the statistics of the Boltzmann-Grad limit. So I stole a picture from a survey lecture by Jens Marklof, and let me just sort of explain informally what we're interested in. Take a lattice, a fixed lattice, which is this lattice in this first picture in this panel, and think about a light beam issuing from a certain point in a random direction. And what we care about is, for a typical direction, it could be some other directions. What we care about is how close does this light ray come to the points in the lattice, which we might think of as being obstacles. That's one question you might ask. And so to say that you're rho close, where rho is a parameter, means that your lattice intersects this long and thin rectangle. Think of rho as being a small number that you're going to care about the statistics as rho gets smaller and smaller. So now you can do the following trick. You can rotate this long, thin rectangle. The direction of rotation is such that it gets mapped to the horizontal. That rotates this original lattice to a rotated lattice where the angle depends on this random initial choice of direction. And then you apply a diagonal transformation that makes this rectangle have the same area, but be kind of standard, a uniform rectangle of size, in this case, 2 by c. It doesn't really matter. Now, what happened to your lattice? Your lattice just changed. And now the way that Marklof-Strombergsson analyze these statistics is they ask how these are now become random lattices, random with respect to the usual measure on the space of lattices that many of you care about and study. And what Marklof-Strombergsson realized was that understanding this hitting statistics, or these distance statistics, lattice points, boils down to understanding how a random lattice in the space of lattices intersects just a fixed rectangle in the plane. Okay, so that's a kind of a very beautiful sequence of works that used this idea. And another situation in which this same idea can be, same renormalization can be used, is in a joint work of mine with Solan and Solomon. And I just would like to, instead of telling you what we did, I just want to mention the problem that we tried to understand, tried to solve, and is still open, and I think is a beautiful problem. It's called the dancer problem. It's been open since the 60s, and it asks the following very simple-minded question. does there exist any set in d-dimensional space, d here is at least 2, so that it intersects every convex set of volume 1. So that means it's, in some sense, it's big because it's intersecting every convex set. But on the other hand, the number of points in a ball of radius t grows like a constant times the volume of that set. So that's a way of saying that the number of points, the point set is not too large. So it's obviously a discrete point set. So this is a wide open question. Nobody knows if such sets exist at all. And using this kind of affine group renormalization, we were able to get some partial information about this. So affine group is relevant here because the condition of intersecting convex sets of a fixed volume is invariant under this group. Okay, so that was my historical description of why one would care about this ASLDR dynamical system. And here's a pair of questions that Marklof and Strombergsson asked. The first is kind of a vague question. What are the possible ASLDR invariant ergodic measures that are supported on discrete sets in the space of closed sets of RD? Just can we write down a list of these measures? That sounds sort of preposterously hopeless because this is a huge space, but I'm going to try and indicate that it might not be a hopeless question. And kind of here, a more refined question, which Marklof and Strombergsson asked, had to do with the application that I described earlier. And it's about equidistribution of these measures. So take a Dirac mass at your favorite discrete set, say it's called Y, and now you randomly rotate it. That's the meaning of this K. K is the rotation group or the orthogonal group. And randomly means you choose K according to the Haar measure on this group. And then you push it by a diagonal element, GT, diagonal flow. And you think about the limit of this measure on the space of discrete sets as the parameter T goes to infinity. So that's clearly an ergodic question. And it turned out, as Marklof and Strombergsson noticed, that this is very important for certain questions in mathematical physics, and that they'd like to describe measures, again, which are ASLDR invariant, and for those measures, they'd like to understand whether these limits can be described. And Marklof and Strombergsson were able to do this in some cases for cut and project sets, and that's what I'm going to describe to you soon, the setup in which they were able to do that. And that's a setup that they introduced, and they rely on the famous work of Marina Ratner and homogeneous dynamics. So we're calling this construction the Ratner-Marklof-Strombergsson construction of measures. Let me tell you formally what these measures are. So we fix the data and the construction of a cut and project set that I had in the beginning of my lecture. So a decomposition of Rn into physical and internal space and the corresponding projections. We fix W, which is our window. Now we define this embedding of the d-dimensional affine group inside the n-dimensional affine group. It's just an upper corner embedding, or another way of thinking about it is these are affine maps of d-dimensional space, and you just let them act on n-dimensional space by acting trivially here. So remember, the physical space is d-dimensional. You act on physical space according to the map, and you just leave internal space alone. So that's the meaning, the geometrical meaning of this embedding. And so this group becomes embedded in this group. And now you look at the homogeneous space, affine group ASLNR divided by affine group ASLNZ. So that's the space of grids in n dimensions. And this space carries ASLDR invariant ergodic measures. One of them, for example, is the Haar measure on this total space. There may be others, which as we're going to discuss. And according to Marina Ratner's work, all of these measures are homogeneous. They have a nice description in terms of intermediate groups H. H is a group intermediate between ASLDR and ASLNR. A priori, it could be ASLD. It could be ASLN, in which case this would be the Haar measure on the space of grids. And given such a measure, mu bar, we're going to project it down to a measure on d-dimensional sets by taking the map that takes a grid and forms the corresponding cut and project set. So that's the construction. So let me just repeat this one more time. We're describing measures. The measures are a way of choosing a cut and project set. The way you choose the cut and project set is you fix the cut and project data. So you fix the direct sum decomposition in the window, but you vary the grid, the lattice in the or lattice or grid in the construction of cut and project sets according to some measure. It could be the globally defined Haar measure on the space of n-dimensional grids, or it could be some other homogeneous measure, which is ASLDR invariant. Having chosen the lattice, you've already chosen the window and the cut and project data. You just apply the cut and project construction, and you get a random cut and project set. Okay, so that's the construction that was proposed by Marklof and Strombergsson.
So how does it depend on the window? You change your window, everything
Changing
changes?
the window changes the sets. It's sort of obvious that there's a close relationship between the measures as dynamical systems, but sort of if you look at the sets that you get, they're going to be different depending on the window. For example, their density, asymptotic density, will change depending on the volume of the window, and so on and so forth. We're going to see that the geometry of the window does play some role in the geometry of these sets, but sort of as a dynamical system, the measures will sort of have the same, will be coming from another dynamical system, so they'll have kind of a common, what is it called? They'll both be factors of the same dynamical system upstairs. Okay. So here's our first theorem from our project. We prove that any ASLDR invariant measure which lives on cut and project sets, in other words, assigns full measure to cut and project sets, has to arise via this construction that was mentioned in the previous slide. So there is no other way to construct ASLDR invariant measures on cut and project sets. Well, there's this word irreducible appearing here that I'm not going to define. If people are interested, I can define it at the end of the lecture. But basically, irreducibility means in a cut and project construction, sometimes you can construct the same set using smaller dimensional objects, like if the lattice, if the projection map into physical space, for example, has a, when you restrict it to the lattice, it's not one-to-one, then that often means that you can describe the same cut and project set with smaller dimensional data. So we rule that out by making this irreducibility assumption. And under this irreducibility assumption, we get this theorem. So I said earlier that the space of all closed sets is a huge space, and it seems kind of hopeless to describe the ASLDR invariant measures on this, all such measures on the space of closed sets. But I want to raise a provocative conjecture and say that actually this construction is the only one supported on Delaunay sets. So what are Delaunay sets? A discrete set in RD is called Delaunay if there's a lower bound on the separation between two pairs of distinct points. So any 2 points are separated from each other by some amount, and also there are no arbitrarily large open patches. So that's a classical definition in the theory of discrete sets, and that's a huge collection still. It's much bigger than the class of cut and project sets. Nevertheless, I'm conjecturing that any ASLDR invariant measure which lives on these Delaunay sets, well, the conjecture says it has a non-trivial joining with an RMS measure. So the way you should interpret this conjecture is it's essentially described by the RMS construction, maybe with some additional randomization tricks, which I can tell you about if you, if you ask me later. I can tell you why I want this added flexibility in the construction. The only constructions that I'm aware of come from the RMS construction and some extra little randomization tricks that don't essentially change the measure. In particular, I don't know of any counterexamples to this conjecture. Okay, I should say that it's a very ambitious conjecture. And I should say that I don't have much evidence for this conjecture either. The only evidence I have is this theorem here, which is much weaker. But I think it's very interesting to find any other ASLDR invariant measure on Delaunay sets, which is different from this construction of Marklof and Strombergsson. I haven't been able to find one. Okay, so that's a side remark that maybe if this conjecture happens to be true, then our classification result actually classifies all the ergodic measures in a very wide class of constructions of discrete sets. Here's a more detailed description of the measures that arise, which is our second theorem. We classify. Remember that in Ratner's theorem, the homogeneous spaces are described in terms of a subgroup H, which is intermediate between ASLDR and ASLNR. The measure is invariant on a closed orbit of H, for some closed orbit of H. And our next theorem describes all those groups that may arise. And they all arise by one of two constructions. You take a base group, which could be SLK for some number k bigger than or equal to d, dividing n. You could take the symplectic group, but you only do that if d equals 2. And then you perform a restriction of scalars construction, which is a classical construction in algebraic groups. For this construction to work, you need the dimension of the total space, the dimension n, to be divisible by this number k, and the quotient number is the degree of the field extension and the restriction of scalars. So if you're not familiar with algebraic groups, the takeaway here is that there's a very, very detailed and very short list of potential examples of such measures. There are really very few of them, and they have a very precise description in terms of algebraic groups. So let me give some examples to sort of illustrate this classification theorem. Suppose you're interested in cut and project sets in 2 dimensions. So D is 2. And M is also 2. That's the dimension of internal space. So the total space is 4 dimensionals. So these sets come about through grids in 4-dimensional space. And with these choices of D, M, and N, there are only 3 cases. First is sort of the big case, or the generic case, where the measure is the Haar measure on the group on the space of 4-dimensional grids. So in other words, H is the 4-dimensional affine group. Or we could have a restriction of scalars construction, but see here that n is 4, d is 2. So the only way to do that would be to have k equal d and the degree to be 2. So that means we're discussing quadratic fields. And if the base group is SL2, H looks like this. It's a block group. It's 2 by 2 matrices with blocks. So let me direct the translations. And we have here also, in this case, a description of the lattices that come up. They come about by as the Minkowski embedding of a ring of integers in a number field. And the third example is the symplectic lattices. And that's also an example. That's also a possibility. You could choose this lattice to be symplectic in your cut and project construction. Okay, so that's an illustration of how what the theorem gives us. And now I want to move on to something I call a crash course on the Siegel summation formula. So I think a lot of people in the audience have been involved with the Siegel summation formula. And we heard Michel Skanderi give a very nice lecture about this in the previous semester, and others. And so what we do in this project in order to use this classification is we carry out the analog results for the cut and project sets. So if you're not familiar with this, you're seeing it for the first time, it might be rather fast, but all the information is up here on the slides. So SLNR over SLNZ I'm now describing the classical case due to Siegel. So S on R over S on Z is the space of lattices. My notation is this curly X of n. Given a compactly supported continuous function on Rn, I define this hat function, or the transform sometimes it's called, via this summation procedure, which is called the Siegel summation formula. The value of the transform on a lattice L is the sum of the values of the original function on the non-zero lattice points on L. So given a function on Rn, you get a function on the space of lattices. And there's a relationship between the integrals. There's a constant C, which depends on normalizations of Haar measures. And up to choosing this constant C, the integral of the original function f is the same as the integral of the transform f hat. So this is a very useful formula. And in fact, it's the only way to get explicit, to be able to compute explicit integrals on this space of lattices. And it was extended. So the purplish text is discussing sort of analog results, which won't be very precisely stated in my talk. But there's an analog result replacing the measure, this measure here, which is the Haar measure on the space of lattices, with a general RMS measure. And this was done by Marklof and Strombergsson in 2014. And in that formula, this is, what you do is you sum, instead of summing the function on all lattice points, you just sum it on all points of your cut and project sets. Zero doesn't play a special role anymore, so you don't have to exclude zero. And you get an analogous formula. And there's a constant that has to be computed, and they also computed the constant. There's a higher dimensional analog, which goes like this. You choose a number p, which is, we're going to be summing on p tuples. So this is the original definition of the transform up here. And we're going to define the pth transform. Instead of summing over all the non-zero lattice points, you sum over p tuples of non-zero lattice points, and you get this new function. And well, first thing to ask is the function that we obtain in this way integrable with respect to the Haar measure on the space of lattices? And Rogers and Schmidt settled that question, and they proved that for p less than n, this function is integrable. P here in Rogers and Schmidt, p was an integer. P could actually be a real number, so q say, and then the original transform f hat will be an LQ whenever q is less than n. And this was proved by Eskin Margulis Moses in 98. And we, in purple, it's our contribution. So we have an analogous formula for our for the transform associated with cut and project sets. So you sum over p tuples of elements in your cut and project set, and we tell you the integrability bound. So, and the integrability, this is sharp, I should have said. So if you let q equals n, the transform is no longer an LQ. We determine the threshold for a general RMS measure. It depends on the Q rank of the group that appears there, which is an algebraic invariant, a classical algebraic invariant. And there's an interesting consequence. If you fix D, which is the dimension of physical space, and you start varying n, you can do that and get different cut and project sets in the same dimension. With n getting larger and D fixed, the internal space is growing and the Q rank could be growing. So the integrability of the transform is increasing. And that's kind of a novel feature that doesn't appear for the space of lattices. So you can take cut and project sets which have higher and higher moments if you care about these things, and many people actually do. And another thing is that Rogers did along with Wolfgang Schmidt, and there's a beautiful treatment also of Andre Weil, Andreevej is something that I want to call, so this is a bunch of papers, it's not one paper, this is a lot of work in the 50s was around proving so-called higher moment identities. And so let me scroll back up. You remember this formula, I'm sorry, you remember this formula here, the Siegel summation formula. You might want to have an analogous formula replacing this f hat with fp hat, the summation on the space of p tuples. And in fact, such formulas do exist, but they're not that simple. And there's sort of a complicated combinatorial formula in the literature for evaluating this integral. It's sort of complicated. Conceptually, it's not complicated. It's sort of it's a sum of nice integrals, but there's a bunch of nasty coefficients to work out, and it's sort of an infinite countable sum over different integrals. So it's sort of combinatorially intimidating, but it's sort of conceptually not that bad. And we get an analogous formula for the cut and project situation. For any RMS measure, we get a kind of a combinatorial formula that works out a precise identity for this integral. And the measures that show up actually, interestingly, also involve something that looks like a cut and project construction. You take an H invariant measure on this space, the space of p tuples. You add this condition that the points map to the window. You restrict your H invariant set to this your H invariant measure to this set, and then you project it. So it's sort of like an analog of the cut and project construction, also for getting these measures. And another thing that happened in the 50s, I guess, or the 60s, probably the 50s, is that Rogers obtained, in the 50s, he obtained this celebrated second moment bound, which was discussed in Michel Skanderi's talk and many other places. So what you care about is the second moment, or the variance, the deviation of the function from its average. And so you square that, and that's called the second moment. And Rogers showed that this second moment is bounded by a constant independent of any function times the supernorm of the function times the expectation. And this is a kind of a technical device that tells you that typically for many, it's a way of proving that for many observables, the value that this transform takes on a given lattice is actually close to the average value, which is something that you might care about. And we proved the analogous. I don't have anything down in purple, but you're seeing that I'm using lambda, which is my letter for a cut and project set. We proved the same formula for cut and project sets, except for a very short list of counterexamples. In Rogers also, the space of two-dimensional lattices doesn't satisfy this bound, and we similarly have a very small bunch of exceptions, but other than those exceptions, we get the same bound. Let me describe an application. So this is following a well-known work of Wolfgang Schmidt from 1960. It's a counting problem. So here's what Schmidt talked about. You take any collection that Schmidt calls an unbounded ordered family. So the sets in this family are Borel sets, and they're indexed by real numbers. And as you increase the parameter, the sets increase. So what you should have in mind as a first approximation could be, for example, balls around a fixed center, and T could be the radius of the ball. But you could also take other sets like, I don't know, intersections of these balls with just the neighborhood of a subspace, or something spiraling, or whatever your favorite notion is of an increasing family of sets. And you want the volume of each individual set to be finite, but the volume to be growing to infinity. And what Schmidt proved for this measure on the space of lattices And what we so there's some noise here, I guess you can hear. So what Schmidt proved for the space of lattices, and we extended to these RMS measures, is this bound. So no matter how you take your sets of so-called balls and let them grow, these are these sets omega t, for almost every choice of your discrete set with respect to the measure, the number of points in the ball grows like the main term, which is the volume times a constant, normalization constant, and then an error term, which is the square root of the volume, approximately. And this theorem of Schmidt is sort of, even though it was proved over 60 years ago, is still state of the art. So there's a kind of there's a conjecture, for example, if you just take Euclidean balls and you say, how does the number of points in a Euclidean ball grow as t grows to infinity for almost every lattice in Rn? This is the best result, even for Euclidean balls. It gives the best error bound. There's a conjecture of Goetze slightly improving this exponent, but that conjecture is still open, and it's an interesting question to try and resolve, even for lattices and for balls. But as I explained, the Schmidt theorem is much more general because it deals with an arbitrary growing sequence of sets. And we prove the analogous theorem for these RMS measures. And what this kind of result doesn't settle is what happens for a concrete cut and project set. It's just talking about almost every, but it doesn't specify the set of cut and project sets that satisfy this this kind of a bound. So we don't know, if you give me a cut and project set, our method doesn't tell us whether this kind of a bound holds for that set. You could ask about specific sets like the Penrose example that I showed earlier, or the other tiling examples that I showed earlier. Other people have looked at these problems, and so I listed a bunch of people and a bunch of techniques here. This is Yair Solomon, who gets actually better error terms, or other error terms, which are often better, for sets arising from substitution tilings. In a joint work with Alan Haynes and Mike Kelly, we used the Diophantine approximation method for this problem, and Scott Schmeeding and Rodrigo Trevino also can deal with another class of discrete sets with some kind of affine self-symmetry, not affine, self-similarity. And they use a technology called pattern equivariant cohomology. So a bunch of people have looked at these error terms. And but this is the first result describing what happens for almost every cut and project set with respect to these measures. And this result has a patch counting improvement. So remember, we had patches at the beginning of the lecture. I showed you the Penrose tiling, and I explained what I mean by a patch. So here's a formal definition of a patch. It's what you see around X to radius R. It's sort of the set that you get in a ball of radius R around the origin if you translated the cut and project set so that X became the origin. So this is what you'd be seeing. So that's called a patch. And you might want to count the occurrences of certain patches in growing balls. And this is exactly what we do. So this left-hand side is the number of times you see the patch P0 centered at a point X, where X is in your growing family, and in a point in your discrete set intersect the teeth element of your growing family, just as we had earlier, except we're adding this new restriction that we want to see a given patch. And so there's a main term asymptotics, which was known before our work. There's a constant that you can compute, and the main term grows like the volume times this constant. And we added an estimate of the error, and so we get a power savings. The error behaves like the volume to a power smaller than 1, where the improvement in the power in the power savings actually depends on the window. So this is the first, Dimitri asked earlier, what role does the window play? In this result, the box dimension of the boundary of the window plays a role. So if the window is nice and regular, you can get a good error bound. If the window is sort of fractally, but not that fractally that there's still a gap here, M is the dimension of the space that the window lives in. So we want the boundary to have strictly smaller dimension. Well, if that holds, then we get this kind of a estimate for the counting problem. Okay, that's the end of my slides. So thanks for your attention, and I'm happy to take questions if there are any questions.
Okay, well, let's give the round of applause to Barak, either virtual or acoustic, I don't know. Yeah, I think it works nice this way. So any questions? At all, we still have time for questions. So there's one thing I wanted to ask. So you have this omega t, which is this family of sets. So what exactly are the conditions in this family?
It should grow. So if you take T1 bigger than T2, then the set omega T1 should contain the set omega T2.
Yes.
And they should all have bounded volume. They should be measurable of bounded volume with volume going to infinity, and that's it. No other conditions.
Okay, so they can their union can be something.
The union can be a proper subset. Yes.
Something kind of very very narrow, stretching to infinity.
Yes. Yes.
And then you'll still
but the union should have infinite volume.
Yes.
Yeah. But remember the order of the quantifiers. You first choose this system omega t, and then the theorem says that almost every lattice or almost every discrete set intersects this omega t with the expected number of points. I mean, obviously, if you took a thin strip, you could find lattices, an infinite thin strip. You could find lattices that completely miss this infinite thin strip.
Yeah, sure, but if you have a thin strip and you have a patch, which is some kind of
so the patch, what we're counting is sort of, the patch doesn't have to be contained in the strip. We're counting the appearances of the center of the patch. So patch
okay, that's what I didn't understand. So you want the center of the patch in the strip, but everything else can be completely outside.
Yeah.
Mm-hmm.
That's right.
And if you want all elements of the patch in this set, then you have to do something else.
Well, exactly like you were saying, the set could be very, very thin, and the patch could be too big to fit inside the set anywhere. So
yes,
then you're in trouble. Yeah, I think the way we're stating the problem is the way that's also been taken by the other people studying it, and I think it's more natural to do that. I mean, you just care about the center. You can think about these patches as kind of like refined colors associated. Every point in the so I should have said, maybe it was obvious, maybe not. The number for any given radius, the number of different patches that you see is actually finite in these sets. That's a property called finite local complexity. And so you should, as you increase t, the radius, you get more and more of these patches, but it's always sort of a finite number of patches. So you could sort of think of, t be equal to, I don't know, 1, maybe you're actually coloring the points in your set with 2 colors. If t equals 10, you're coloring the points in your set by 50 colors. As you increase, and basically you're asking, how did the what's the frequency of the sets in a given color?
Okay. Other people want to ask something? Okay, so if you basically, if I ask you to give one sentence, or let me try to give a one sentence summary of your talk, and then you'll tell me whether I'm wrong or not. So you need to study those cut and project sets, their distribution inside some subsets of RD. So you look at this cut and project set and you lift it to the actual lattice, and then you have orbits of these lattices, and then you just study dynamics on the space of lattices upstairs, apply some Siegel-Rogers formulas to get some bounds, and then you project down, and that's your answer. Right?
Yeah, as a first approximation, that's a pretty good answer.
Okay,
but
works for me.
sort of to begin the discussion, you need to, when you lift upstairs, you need to think about which homogeneous spaces do you see. So like, as you know very well, many people in the audience have been studying Siegel summation formulas for G mod gamma, which are not SL and R over SL and Z. So our first result is this classification result, which gives us a very concrete list of G's and gammas, which are these groups obtained by restriction of scalars. And so we need to prove these Siegel summation formula type results for these particular G mod gammas, which had not been done before. And that's kind of the main tool. And once we have that tool, it's exactly as you say, you sort of analyze what's happening in the space of cut and project constructions by understanding what's going on upstairs.
Okay.
But sorry, Amir here.
Hi, Amir.
How are you? Sorry.
Good to
So
see
for
you.
two, good to see you. Maybe. You can actually see me.
That's
Oh, all right. Good
even
to see
better.
you too.
Even
Yeah,
better.
good to see.
Yeah.
Yeah. So for these analyzing these Siegel functions, it's not you don't do system of inequality. This isn't the big space, right? It's just somehow
Right,
integrability in the big
so
space. Yeah.
we don't do this. We don't need the system of inequalities. We don't prove like what EMM proved.
Right. So it's reduction
EMM,
theory mainly.
Right, it's reduction theory. So we have to do reduction theory in these spaces, exactly. It's just reduction theory for that step, yes.
Yeah.
I mean, there's a big initial step, which is sort of algebraic group steps, like just identify the groups that appear in Ratner's theorem for this particular embedding. We have that embedding of ASLD sitting inside ASL and R, which orbit closures could show up.
Yeah.
And that's sort of a long discussion, analyzing algebraic groups and cutting down the list to a very, very small list. And once you have that, like you said, it's reduction theory on these quotients, on these restriction of scalar quotients. And then there's some nasty part. I mean, the Rogers technique is not that simple. So, okay, anyway, I invite you to take a look.
Integrability is difficult. Yeah, the L2 integrability is difficult. This is,
yeah.
Thank you.
Sure.
Oh, sorry, I was muted, I guess.
Any
other questions? Do we want to say something?
Yeah, just a more of a clarification that I think was answered by the previous discussion, but just to make sure.
Yeah.
All lattices are also examples of these cut and project sets, right?
Right.
But, so you could say you gave like another proof for all these formulas for lattices.
It's the same proof.
Yeah. Okay. So it's the same proof.
I mean, okay. I guess for lattices, there are several proofs. I guess it's not one proof, but the proof that we follow is the Weil. So Weil has a very nice. André Weil has a very nice write-up presentation that works for general algebraic groups, and we follow his technique. I don't know if I don't know if you're familiar with it, but I mean, there's a couple of proofs of this Siegel summation formula and these identities, and they all involve. They sort of in the literature they become gradually more and more axiomatic. So somehow in Rogers and Schmidt they're more combinatorial, and in Weil they're very, very nice and axiomatic. So we kind of try and follow the Weil approach. Once you have the integrability, like Amir said, integrability is an important point. You have to do some work with understanding the structure of the cusps in these quotients, and you get the integrability result. Once you have integrability result, you can sort of feed it into Andre Weiss formalism, and you kind of get an abstract identity between two integrals, where the identity involves some constants, which are a priori hard to evaluate when we don't evaluate them too often, and also some list of, say you're doing the second moment bound. So you're interested in pairs of vectors. So the measures that are going to show up, you have Rn cross Rn, you have the Lebesgue measure on Rn cross Rn, and then you have sort of measures that lie on rational subspaces of n dimensions in Rn cross Rn. And each one of those Lebesgue measures could show up, and it should also have a normalization constant. And that's all sort of built in very nicely to the Weiss formalism. And it translates into some question about certain homogeneous measures in sets of the form G mod H for various H's. And there's an extra twist here in this cut and project system is you want to take these measures on G mod H and you want to analyze their effect on the cut and project picture. You have to sort of push them down. They live in Rn cross Rn, and you have to push them down to Rd cross Rd. So that's sort of an extra complication. But I mean, sort of the basic strategy is the same as in Andre Weiss.
And then I have a follow-up question. So for the Rogers' original formula, if you replace in the Siegel transform summing over all lattice points by summing over primitive lattice points, the second moment formula simplifies drastically, right? You kind of lose all this combinatorial thing of identifying.
In the case p equals 1, it simplifies drastically, but in case p equals 2, it's
for the second moment.
Right.
The second moment where it simplifies after higher moments. So is there an analog for the replacing all lattice points by primitive lattice points when you do the catching?
Yes, that's also in the Weiss. So basically the way to think about it is instead of, you just think of primitive lattice points as being just a gamma orbit. So you start with, say, SL and Z acting on Zn, and you think of primitive lattice points as being one orbit for SL and Z. And in the general case, you have SL and Z acting diagonally on Zn cross Zn cross Zn, P copies. And you care about the SL and Z orbits on this space of P tuples. That's not this is not anything that we did. This is not our contribution. This is all sort of implicit in Andre Weiss' point of view.
But you never fix the origin, right? Your objects are always affine invariant or something. So there is no notion of
no. That's not really the correct. We don't fix the origin in the cut and project sets, but when we do the lifting upstairs, somehow the origin plays a role. So we kind of have to figure out how many of these points arise from the origin. Basically, it's just the same. You have to figure out the gamma orbits, the SL and Z orbits in Zn cross Zn cross Zn P times. So in some of these orbits, 0 is an element of one of the elements of the P tuple could be 0. The origin could show up. So the answer is yes and no somehow. I mean, on the level of the cut and project set, the origin doesn't play a special role. But when you pull the picture back up to well, let me answer the question this way. You could talk about the Siegel summation formula in the space of lattices and allow the 0 as add summation at 0 as well to your definition of the transform. And then you'd have the same identity, except you'd have an extra term. Like you'd have a constant times the integral in the space of lattice plus another constant times f evaluated at 0. F evaluated at 0 being that's like the Dirac mass at 0, which is another SLNR invariant measure on Rn. It's sort of a trivial one. So similarly, you have the SLNR invariant measures on Rn or on products of Rn with itself P times, and that's sort of the object that you think about.
Yes, but okay, go ahead.
Oh yeah, I just wanted to ask, how would it be possible to compute these constants like using Poisson summation the way Andre Weil does in your context, or no?
I think it would be very interesting to do and challenging, and I don't think it's hopeless, but we certainly have not done it. I definitely would be very happy. I think that's a very good thing to try and do, to compute these constants. I don't know whether the particular technique, I don't know about whether Poisson summation formula is the best way to go, but just evaluating these constants. Actually, there's a bunch of techniques for evaluating the constants that people have used. I think that's a great type of question to try and do.
Any other questions of great type or some other type?
I also wanted to ask you a question about the version of the conjecture for the Delaunay sets. I mean, you mentioned there is another source of randomness that can be.
Yeah, imagine the following silly example. So you take you randomly choose a lattice and you multiply it by 2. So inside the lattice, you're looking at, there's a certain subset of points which are multiples of lattice points by the factor 2. So if you were to erase all of those points, you'd still have like the odd points in your lattice. That would still be a Delaunay set. And so that would be kind of a silly source of an example. You would take the lattices, so the primary randomization mechanism would be to choose your lattice at random, but then you sort of strike out some of these points. Another thing you could do is you just could take all the even points and Bernoulli toss a coin independently, IID, for each one of those points to whether or not to keep it or delete it. You'll be constructing a Delaunay set randomly, and you can check that this is, has the properties that we wanted in the conjecture. But okay, in some sense it's cheating. The basis of the whole thing is the measure on the space of lattices, and then you're performing extra tricks to remove some of the points. And that's sort of my conjecture, that the only ways to take an ASLDR invariant measure on the space of Delaunay sets would be to take one of these cut and project instructions and maybe sort of artificially randomize some points and delete some points at some kind of random mechanism. That's the only type of example that I know.
Thank you.
Okay, anybody else? So is there such thing as p-adic Penrose tiling or as arithmetic
yes.
things?
So let me check now that I'm no longer. I'd like to check whether Daniel Elbaz is here. No, I guess he's not here. So Daniel Elbaz's thesis, some of you may know Daniel Elbaz. His thesis was about the adelic cut and project construction. So even in the cut and project literature, dating back to the 60s and 70s, people did work with other locally compact abelian groups like p-adics and finite s-adics, so finite products of p-adics. And then Elbaz's thesis, he worked with the ring of Adels, and you get very interesting sets that way. For example, he showed that the set of primitive lattice points is an adelic cut and project set.
Interesting.
Yeah, so there's lots of room for taking that whole theory to the sort of the p-adic, s-adic, and adelic worlds. I think that's very interesting.
All right. So, well, let me thank Barak again and hope he'll join in this round of applause.
Thank you.
Virtual or not. And let me stop the recording now, after which we can maybe do something unofficial.
Go for a drink.